It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Iced Coffee.
Hi guys, hope you're having a great day. Mine's just been awesome. If you want to know why, you can see that, look at that, look, Farmers Union Iced Coffee, 2 litres for $2, look at that. Woo. Hold it steady, there you go. If that doesn't make for a fantastic day, the only thing that would make it better apart from buying it for $2 is drinking it. So excuse me for a second. 10 o'clock at night while I'm recording this, so I'm pretty wired. I'm going to have lots of fun. Hopefully you guys have lots of fun while you're watching this as well. So this is the next video in topic 4. I'm doing things a little bit differently to how the SACE curriculum has it, so I'm doing 4.4b for metals. So the previous video, which I will have finished for this, will have just gone and looked at fuel cells and flow cells and electrochemical cells. And so what we're doing is we're following straight on from that by looking at electrolytic cells. Now, electrolytic cells kind of are the reverse or the matching pair, if you like, to electrochemical cells. So where an electrochemical cell will take a spontaneous chemical reaction to produce electricity, electrolytic cells require electricity to produce a chemical reaction. And the chemical reactions we're looking at are non-spontaneous ones. That means they won't readily occur unless we put energy in. Now, in particular, what we're going to be focusing on is using this to extract very reactive metals from their molten state, right, or reactive metals from that aqueous solution. So I'll look at that in a little bit more detail. But basically, to give you a summary, here's an example just of a general electrolytic cell. All right, you can see here that still we've got oxidation at the anode, we've got reduction at the cathode. That doesn't change from an electrochemical cell. Okay, the cations still flow towards the cathode, anions towards the anode. Okay, we've got an electrolyte, but one of the main differences is that instead of 2 half cells, so we had like a half cell over here and a half cell over here, we've now got 1 cell where everything is contained. And the other main difference is that we've now got a power supply. Okay, so where we used to have an ammeter or a voltmeter or something to take the load of the electrons that we're producing, now we're putting electrons in. When you've got a power supply like this, the big line is the positive, small line is the negative. And what that means for an electrolytic cell is that the polarity of the electrode swaps. So back in an electrochemical cell, the anode was negative. Here the anode is positive. And the way I always tell my students to remember that is GAN-EAP. Alright, that term GAN-EAP, I think I went through it in one of the previous videos. In a galvanic cell, the anode is negative. In an electrolytic cell, the anode is positive. So if you remember GAN-EAP, G-A-N-E-A-P, it's an easy way to remember it. Okay, so here's a quick summary for you. Okay, the energy change is electrical to chemical. Anode is positive, cathode is negative. Electron flow is still anode to cathode. Oxidation occurs at the anode, reduction occurs at the cathode. Okay, so the only thing that's really different is this polarity here, and that the energy change is electrical to chemical. Alright, we use electrolysis for 4 main reasons. One of them is for electroplating. So quite commonly where you'll see this in the world is things like galvanized iron. Any metal that tends to corrode reasonably quickly will generally have a protective coating over the surface of it. So what we'll do is we'll put a reasonably, sometimes probably more reactive metal over the top, let that reactive metal form an oxide coating. That oxide coating then becomes quite impervious or resistant to water and moisture, all those things which will cause corrosion, and that protective layer will protect the metal underneath. So galvanized iron has iron as the main part of the fencing or the roofing, but then they put a coating of zinc over the top of it. They plate it on using electrolysis, and that zinc reacts with the air to form zinc oxide, which protects the iron underneath from rusting. This, as I said, is the main one we're going to focus on, though, is extraction of metals. So from the molten salt or from the aqueous solution, we'll talk about which ones come from which in a minute. You can also use it for electrolytic refining, so that's purifying of metals. Copper is mainly the main one they use there. And the other one you can use is for production of chemicals. So the diaphragm cell is an electrolytic cell which produces sodium hydroxide, chlorine and hydrogen all in the one cell. Now that's good because sodium hydroxide is the basis for a lot of cleaning agents. It's called caustic soda. You'll find it as oven cleaner. So it's very, very useful in a lot of other chemical reactions as well. Chlorine gas is used in water purification. We'll look at that later in this topic. And hydrogen is quite useful in industry as well, and it's also used for making margarine. All of those come from basically electrolyzing a concentrated solution of salt water. So that's a really, really useful electrolysis reaction you can do as well. So if we're looking at extraction of metals, okay, here we've got an example of some metal reactivity going from really high down to low reactivity. All right, so potassium, sodium, magnesium, aluminium are all classified as highly reactive metals. Okay, and so you'll find these combined in nature with other things, normally oxygen, sulfur, things that are abundant in the earth. Okay, so aluminium, for example, is found as aluminium oxide or bauxite, Al2O3. Okay, zinc is found as zinc blende, ZnS. Okay, sodium, obviously sodium chloride, you'll find that. Iron is found as iron oxide. So when they're reactive, you'll find them combined with other things in nature. And if we want to get that metal out, so if we want to extract aluminium or zinc from its ore, we need to do electrolysis. Okay, when you come down to these really unreactive ones, like mercury, silver, and gold, okay, they're generally, you just have to heat them and you'll get them from their ore, or sometimes like gold, you can just find them on their own, which was why they were so valued early on, because they didn't require any extraction. So what we're going to be looking at is the electrolysis of the molten salt. So that means you're needing to actually heat up and melt the salt with nothing else in there, and then electrolyze it, which is quite an expensive reaction. Or we're looking at electrolysis of the aqueous solution, which we do for zinc, okay, or what's called carbon reduction, which is something we do for iron. You can do that when it's not a highly reactive metal, but more intermediate. So, as the reactivity of the metal increases, we said the amount of energy required to remove the metal from the ore increases. All right. If you use electrolysis, you're supplying electricity, so there's a cost there. Okay. If you're doing electrolysis of the molten salt, you have to heat it to generally very high temperatures, okay, which also requires energy and cost. So if basically in industry you want to extract the metal from the ore the cheapest possible way. So if you don't have to use the molten salt, you don't use it. So four main stages that we look at here. First one, sometimes you might need to concentrate the mineral. So when we're talking about a mineral is how you find it combined in the earth. So the aluminium oxide or the zinc sulfide, for example, you might dig it up from the earth, and you might dig up 20 tons of dirt, and there's only like a quarter of a ton of your mineral in there that you want to be able to use. Now there's no point transporting that 20 tons to your factory. So what you do is a concentration process, and what they'll do is leave behind all the unwanted rock, which is called gangue. Okay, and quite often that's really useful to do at the site, because one, it reduces your transport costs, and number two, it allows you to then refill the ground that you've dug up. Excuse me for a second while I get some hydration. And so quite often what they use is something called froth flotation. Froth flotation basically involves putting air through the bottom of your mixture. What happens is your mineral sticks to the surface of the air and rises to the top, and you can scoop it off, and all your unwanted rock, your gangue, is left behind, and you can just basically filter it off or scoop it out and put it back into the ground. So you do that if there's a relatively low concentration. You don't want to take all the unwanted or useless stuff back. Sometimes then you might want to convert it, and probably zinc is a really good example of this, because zinc is found as zinc sulfide. Now if you electrolyze a solution with zinc with a sulfide in there, quite often you get sulfur gas formed, which can form acidic solutions, which can corrode your electrodes. Obviously also sulfur dioxide gas, which is quite poisonous, so you don't want to be electrolyzing something that's going to be quite harmful. Okay, so what they'll do is they will convert it into something like an oxide or a sulfate, and in solution, when you electrolyze that, it's less harmful products. Sometimes you don't even have to do these two steps. Sometimes you can just go straight to the next step. So aluminium is a good example. You don't need to concentrate it because it's relatively high in concentration where it is. You don't need to convert it because it's already oxide. And so you go straight to the next step, which is the reduction step. Okay, reduction is the electrolysis. So metals will want to gain electrons, okay, and so that they undergo reduction. That'll be at the cathode. So the metals are always produced at the cathode. Okay. The final step, once you've done your reduction, either of the aqueous or the molten solution, is the refining process. Okay, refining is sometimes if you need to purify. Normally when you do your electrolysis, if you've gone through and got rid of your impurities reasonably well in the first stages, the product you'll get at your cathode is reasonably pure and you can just use it. Sometimes though they will use electrolysis to just refine it and get a very high quality pure metal, because sometimes if you've got impurities in there, it can lower the quality of it. So it's used rarely, but it is sometimes used. This is really the main step, the reduction here. Okay, and as we've said, not all stages require, not all metals require all 4 stages. All right, some of them you can just go straight and do the reduction. That's all you have to do. So I'm going to have a look here at the production of aluminium from its ore. So as I said, it comes from the mineral bauxite, Al2O3, and it is a very reactive metal, which is why you find it combined. All right, so you can only use the electrolysis of the molten salt. If you do the aqueous salt, what you've got in an aqueous solution is you've got your salt and you've also got water. Now, water contains hydrogen ions in there. Hydrogens aren't a metal, so hydrogens are much happier to receive electrons to form hydrogen gas than a metal is. So let me just draw that for you to show what I'm meaning here. So you've got hydrogen gas. Okay, here, you've got hydrogen ions in solution which come from water. All right. 2 of those will quite happily pick up 2 electrons, okay, from the anode to form hydrogen gas. Now, as I said, because that is not a metal, that is much more happily, readily able to do that, and so this reaction will occur in an aqueous solution if you have a highly reactive metal, because this is far more energetically favourable than trying to force a metal such as aluminium to accept electrons. So the way that you get around that is by doing, as we said, the molten salt, and because then you've only got aluminium in there, it's the only thing that can happen. So the first step they do is purification of the bauxite. So remember, we didn't need to do a conversion, all right? And this is just depending upon where you get it from. So if this is in Australia, you probably do this purification because we've got high amounts of silicon dioxide and iron oxide in our ground. So what we do is we add sodium hydroxide in. Silicon dioxide. Let's start with iron oxide here. This is a metal oxide. All right, metal oxides are basic. All right, so if you add a base in, this isn't going to react. Okay, there's going to be no reaction here. However, the silicon dioxide is a non-metal oxide. All right, that's acidic, so that's going to react with the base. So our silicon dioxide here reacts with the hydroxide ions to form mobile silicate. So this is sand, which is quite insoluble, unreactive. Silicates here are quite mobile. It forms a glass-like material that we can get rid of. Aluminium oxide is amphoteric, so it will react with an acid and a base. So that will react to form this sodium aluminum hydroxide substance here. As we said, the iron oxide won't react, so we can just get rid of that. And the silicon dioxide is this thick glass material, so we can pour that off as well. And we're just left with our aluminium in there now in a slightly different form that we can use. And so what they do is they just convert that back here. They convert that back to the aluminium oxide here, which they can then use for the electrolysis. Al2O3 is called alumina. Okay, in honour of my good friend Cameron, who's one of our exchange students here at the moment. So alumina, or aluminum is what you call it, but we call it aluminium here. You just have to accept that we're right and you're wrong. So the aluminium we've got here, we can electrolyse that. And what we use is this big container here. So we have these anodes, graphite anodes, which we put inside. They're graphite, which means they conduct electricity, but they don't take part in any reactions. They're inert. Okay, and we have a graphite cathode here as well. Okay, the cathode here is where our aluminium is going to be produced by this reaction here. Okay, so aluminium oxide, aluminium ions in here. So we've actually got Al3 plus here. Okay, you can simplify this equation sometimes if you want by having Al3 plus 3E minus, okay, to give us aluminium. All right, that's another way of writing this equation. This is just showing it from the aluminium oxide that we've actually got in there. But what we'll do is we heat it up, and to about 950 degrees there, so we get the aluminium oxide in a molten form. Okay, we pass the electric current through. You can see bubbles here at the anode. That's going to be our oxygen gas. Okay, and we're going to get molten aluminium down the bottom, which is heavier, so it's going to sink to the bottom, and you can just not filter it out, but just pour it out through the bottom. The main problem here is that these graphite, this is carbon, it reacts with the oxygen formed here, and that slowly decomposes those anodes, so they need to be replaced reasonably regularly. The cathode, because the oxygen's away from it, lasts a lot longer. The other one I'm going to look at as an example is zinc production. So went through zinc production a little bit before in the last topic. There is a YouTube video here which I'll hover over that you can see the link there if you want to have a more in-depth look at zinc. But I thought I'd put this in as a flowchart, because one of the things you do need to be able to look at and do now is to be able to identify things from a flowchart. So basically you can see here we mine it. When we mine it, we're mining zinc sulfide, and that's got about 2.4% zinc in there when we mine it up. We crush it to increase the surface area. We dissolve it in water and do froth flotation, which gets rid of all the waste material. And you can see now we've now got a zinc sulfide or zinc blend concentrate of about 25.7%. We bring air in, which supplies oxygen, O2. That oxygen converts the zinc sulfide, into a zinc oxide, which is far more beneficial for us to do some electrolysis. Okay, leaching is a term for dissolving into something. All right, so what we're doing is we're taking zinc oxide, we are dissolving it in sulfuric acid to turn it into zinc sulfate. Okay, and then what we do is we go through solution purification, which looks like a fancy.
No,
Sorry, accidentally hit pause rather than I was trying to change to black. I'm just going to go to blue. Sorry, that should be solution purification. Okay, and that takes out metal residues. The main ones we've got are silver and cadmium. Okay, if we leave those in, they will be formed at the cathode in preference. Okay, oh look, there's the N that we need. Alright, and there's the S that we need over here for electrolysis. So apologies for my super dodgy slide here. Okay, but we then go through electrolysis, where at the cathode we get zinc ions, picking up electrons to form solid zinc. That gets deposited at the cathode. We just strip that off, and we've now got up to 99.98% zinc. So obviously no need for further purification through electrolysis, okay, because we started with 2.4% and we've gone up to 99.98% zinc. As I said, watch this video if you want a bit more help about it. So this one's all about electrolysis, in particular around extraction of metals from their ores. I'm probably going to do a little separate video just going through that process again about what we will use, what process we use to extract metals from their ores. So have a look for that one when it comes up as well. I think it's just going to be called extraction of metals. So have a look at that. As always, if you've got any questions, ask. And as always, drink the iced coffee. Thanks guys, have a good one.